Hello, sir. Your voice is, you are muted, sir. Please unmute yourself.
Is everything okay now? All right. So suppose T is the map which sends every vector V to itself. That means T is identity map, and you can easily see that this is a linear transformation. And naturally, if you want to see the eigen value, suppose that lambda in F be such that Vt is equal to lambda V, then since Vt is V itself, so V is equal to lambda V, and that makes 1 minus lambda V is 0. So if there is a non-zero vector, if V is non-zero in V, such that 1 minus lambda V is 0, then we know 1 minus lambda has to be 0, or that lambda is equal to 1. So what we get, that lambda is equal to 1 is the characteristic root, and any non-zero vector will be corresponding characteristic vector. So lambda is, and that is the only eigenvalue that you can see. Hence for t equal to say I, the eigenvalues or the characteristic roots are lambda is equal to 1 only. Only one characteristic root. And any non-zero vector V in V R2 over R, that is V is equal to say xy, it's not 0 means not 0, 0. That means both of them are not 0 at the same time, is a characteristic vector of T associated with the characteristic root lambda is equal to 1. Now this example can be extended to, so example 2, therefore let us say T vector space Vf to Vf, and let us take that the dimension of vector space V over F be n finite, and V goes to Vt, and Vt let us say V for all V. Then this T is again the linear transformation. T is the linear transformation is the identity linear transformation. And once again, the same way, if lambda in F is the characteristic root of T, then there exists a non-zero vector v in V such that Vt is equal to lambda V will imply that lambda is equal to 1. As we have proceeded earlier. So this gives that the identity linear transformation on every finite dimensional vector space has only one eigenvalue, namely lambda is equal to 1, and any means every non-zero vector V in V is a characteristic vector of T associated with this eigenvalue lambda is equal to 1. You can also extend this example to, so let us say T here the vector space V over F2, the vector space V over F, V goes to Vt. Vt is, let us say, alpha V. Dimension, let us say V over F be n finite, and alpha is in F fixed, say for example. But any alpha can be there, but for the example, you can take this alpha is fixed. So you can define this map as T alpha. So what the T alpha map is? Alpha V for every alpha. Now you can see that this map sends every vector to scalar multiple of V by alpha. And then you can prove this that T alpha is actually the linear transformation alpha times I, and the characteristic roots you can see of T lambda is equal to alpha. And again, any non-zero vector V in V is characteristic vector of T associated with the characteristic root lambda is equal to alpha. The linear transformation T alpha which is alpha I is called a scalar linear transformation. So alpha times identity is called scalar linear transformation. Now next example, let us take example 4. So let me be the vector space of dimension 2 over the field F. So you can again take, for example, let us say V to be R2 over R, so it will be specific. And the map be defined, say Txy, T, V to V. So V is R2 over R, and therefore you can take V to be, let us take Xy into Vt, and define this Vt to be, say for example, X plus Y and Y. If you define like this, then T is a linear transformation. This I leave for you to verify. T is a linear transformation that I leave for you to verify. So please verify. All right, once you have verified that this is a linear transformation, now we want to see if there is a characteristic root, and if so, then what are the corresponding. So lambda equal to, say, a vector here f is Rn. So be a characteristic root of T. Then naturally there exists a non-zero vector V in V such that V is R2 over R. Such that Vt is equal to lambda. Okay. Now Vt is equal to lambda V means what? Vt is defined as. So for V, you can write as coordinate y. So this is non-zero in V. This makes that x, y, t is lambda x, y. And t is defined as x plus y, y, lambda x, y. And that means this is x plus y, lambda x, lambda y. Good. Now we know that in our pairs, two ordered pairs are equal if and only if the first coordinate is equal to the first coordinate of the other, and the second of both are also equal. So that is if and only if x plus y is lambda x and y is equal to lambda y. Now this y is equal to lambda y means this naturally means 1 minus lambda y. 0. Now this implies lambda is equal to 1. This implies lambda is equal to 1. Otherwise, what will happen? Y will be 0. But if y is 0, then what will happen? From the first equation, and this will imply that x plus y is equal to lambda x becomes y0. So this is x equal to lambda x. So that will force that this is once again 1 minus lambda x is equal to 0. And this will mean that lambda is equal to 1. Lambda is equal to 1. Otherwise, x will be equal to 0. So if lambda is not equal to 1, then and of course this will mean that xy is 0, 0. Because y is already 0. So if y is 0, in that case x also turns out to be 0 unless lambda becomes 1. So this is a contradiction. So what we get here is that hence lambda is equal to 1 is the eigenvalue. Only characteristic root of P. Corresponding eigenvector we want to see. So what is the map T? V is R2 over R. V defined by V is say xy going to say dt, that is xyt is defined as x plus y, y. All right. Now, for this linear transformation, what we see that so this then T is a linear transformation here, and the characteristic root or roots of T are lambda is equal to 1 only. There is only one characteristic root, that is lambda is equal to 1. Now, corresponding characteristic vectors. So let us take v x y, which is not 0. That is x y, which is not 0, 0. X and y are not 0 at the same time. Okay. Be a characteristic vector of t with respect to the characteristic root, say lambda is equal to 1. So that means what? Therefore, what we have here is Vt is equal to lambda t. Vt is equal to lambda v. That means that xyt is lambda xy, and lambda is equal to 1. Since lambda is equal to 1, so we get xyt as xy. That makes that x plus y, y. These first coordinates are to be equated only, second as they are same, so that makes that x plus y is x. So that makes y is equal to 0, and x is arbitrary. But not 0. So what is the characteristic vector? And so x 0, where x is non-zero, is a characteristic vector t with respect to lambda is equal to 1. So the characteristic vectors here is every vector x0, where x is not 0, is a characteristic vector for this. So we take one more example, and then we shall move to something else. Now let us take this example. Before that, note that a T linear transformation is completely determined by its effect on the basis vectors. Now, that is for, let us say, V over F be a vector space over F of, let us say, dimension n with a basis. Let us take the basis B, V1, V2, V over F. And let T be a linear transformation of the vector space V over F. Now to know T, that means we want to know Vt. Then Vt is known if Vit is known for every I, 1, 2, n, and vice versa. Naturally, Vt is known, Vit is known, because Vi is one of the vectors. And if you know Vit for every vector V in V, V can be written as a linear combination of these basis vectors. And if V is a linear combination and T is a linear transformation, then Vt is basically alpha V1, alpha n Vn. T is same as alpha 1 V1 T, alpha n Vn T. So if you know each Vit, you know Vt. And converse, of course, is straightforward. If you know Vt, you naturally know Vit. So for a linear transformation, to define, there could be two ways. One is that you simply can write the image of Vt, image of V under T, that is Vt. Or you can write each Vit and can find out Vt for arbitrary V. So now let us take next example. So let V be the vector space R2 over R, and V be a basis. Be a basis for V over F. F is R. This could be standard basis or could be any other basis. So if T in AFV, that means T is a linear transformation, defined by on the basis vectors, say V1T as V1 plus V2 and V2T as V1 minus V2. So there is a little change from the earlier example. So here we have this linear transformation defined by this. Then find out all characteristic roots of T in F and corresponding characteristic vectors of T. So this is the problem that we want to solve. So now say for let us take lambda in F be a characteristic root of T. And let us take V in V be a corresponding characteristic vector of T. So V is non-zero such that Vt is equal to lambda V. Right? Now first we can determine this linear transformation. So first we determine the linear transformation T. So let us take V to be the linear combination of the basis vectors. Yes. So this is for some alpha 1, alpha 2 in F. Then Vt is what? So Vt will be alpha 1 V1 plus alpha 2 V2 under T. Okay, so alpha 1 V1 T plus alpha 2 V2 T. Alpha 1 V1 T is V1 minus V2. Alpha 1 V1 minus V2 plus alpha 2 V1 plus V2. So you can write this as a linear combination of V1 and V2. So this you can see that alpha 1 V1 plus alpha 2 V1, that is alpha 1 plus alpha 2 V1. And for V2 it is alpha 2 minus alpha 1.
So V1
So V1T is actually V1 plus V2 and V2T is V1 minus V2.
Actually, उल्टा लिख दिया मैंने V1 plus V1T is this and this is minus. चलिए धन्यवाद. So V2T is V1 minus V2. So the linear combination that we get is alpha 1 plus alpha 2 V1 plus alpha 1 minus alpha 2 V2. So what we have got here is that Vt is equal to alpha 1 Vt become alpha 1 plus alpha 2 V1 plus alpha 1 minus alpha 2. Now if V is eigen, so this is what is the linear transformation, and if V is so if V is characteristic vector of the characteristic of T with respect to the characteristic say, root lambda, then Vt is equal to lambda V. Here in this context we will make that this is lambda V. So this is alpha 1 plus alpha 2 V1 plus alpha 1 minus alpha 2 V2 is equal to lambda alpha 1 alpha 1 V1 plus alpha 2 V2, And this is same as here lambda 1 alpha 1 v1 plus lambda lambda के साथ तो 1 नहीं है भाई. This is lambda alpha 2 v2. So that makes that lambda alpha 1 minus alpha 1 minus alpha 2 v1 plus lambda alpha 2 minus alpha 1 plus alpha 2 v2 is 0. Since v1 v2 are basis vectors, they are linearly independent. Therefore, what we get is each coefficient should be 0. So this makes that you have so lambda alpha 1 minus alpha 1 minus alpha 2 is 0, as well as lambda alpha 2 minus alpha 1 plus alpha 2 is also 0. Or you can write that this is coefficient of this. Let us say this is lambda minus 1 alpha 1 minus alpha 2 is 0, and this is lambda minus 1 and this is alpha 1 ही पहले लिखना चाहिए. So this is minus alpha 1 plus this is lambda. So this is your lambda plus 1 alpha 2 is 0. This one equation and this equation number 2. So we have got a system of linear equations in alpha 1 and alpha 2. And this system of linear equation has non-trivial solution because we are looking for a non-zero vector v. So alpha 1, alpha 2 both must not be 0 at the same time. So this system has non-trivial solution if and only if this system has a non-trivial solution for alpha 1, alpha 2 if and only if lambda minus 1, lambda plus 1 minus 1 is 0, or that lambda square minus 2 is 0. That is lambda is plus minus square root 2. As the characteristic roots of t are root 2 and minus. So these are the two characteristic roots. Now we want to see the corresponding characteristic vectors. For each of them. So suppose we have a characteristic vector first corresponding to root 2. So if B, so B is in V and B is a basis having basis vectors V1, V2. So let us take that this is beta 1, v1 plus beta 2 v2 is a characteristic vector of t with respect to the root lambda is equal to square root 2. Then what shall we get? And v is not 0, that means beta 1 and beta 2 are not 0 at the same time. And this Vt is equal to lambda v. That means what? Vt is equal to root 2 v. So for Vt you can write this is beta 1 v1 t. So this is beta 1 v1 plus beta 2 v2 t is equal to root 2 beta 1 v1 plus beta 2 v2. That makes that this is beta 1 v1 t plus beta 2 v2 t equal to, so this is root 2 beta 1 v1 root 2 beta 2 v2. v1 t is v1 plus v2. So this is say beta 1 v1 plus v2 plus beta 2 v1 minus v2 is same as root 2 beta 1 v1 plus root 2 beta 2 v2. What do we get here now? As a linear combination of bit v1 and v2. And once again we shall use that v1 and v2 are linearly independent since they are basis vectors. So this will again, as earlier, reduce to a system of linear equations. So what we get is, so we shall get this. So root 2 minus 1 beta 1 minus beta 2 is 0 and minus beta 1 plus root 2 plus 1 beta 2 is also 0. Good. You can also see that we have a relationship with among beta 1 and beta 2. So from 1 you can have that beta 2. So from this equation 1 you can have beta 2 as root 2 minus 1 beta 1. And beta 1 can be taken as beta 1. So this beta 1 as such. So beta 2 here, these satisfy these two values are satisfy the system of equations. What we have just now seen our system. As the characteristic vectors T corresponding to the characteristic root lambda is equal to square root 2 given by V is equal to alpha 1 V1 plus, sorry, we have written this as a linear combination. So alpha 1 V1 plus alpha 2 V2 as alpha 1 V1 plus square root 2 minus 1 alpha 1 V2 perhaps betas. Yeah? Sorry, so let me change this to beta. Beta 1, beta. And this you can rewrite this as, so the coefficient here, you have beta 1 only, so this is beta 1, and this is v1 plus square root 2 minus 1. For every beta 1, non-zero. Every non-zero, because the beta 1 is 0. This is 0. So this is the characteristic vector. Likewise, you can obtain characteristic vectors similarly for lambda is equal to minus v. Sorry. So we have found the characteristic vectors. So what are the characteristic vectors? For every beta 1 not 0 in F, beta 1 times v1 plus square root 2 minus 1 v2. So if we want to see the characteristic space or the eigenspace of root 2, is the space spanned by or generated by v1 plus square root 2 minus 1, and this is the eigenspace or characteristic space associated with the eigenvalue root 2 of t with respect to the eigenvalue 2 is the subspace spanned by or generated by the basis. Basis can be taken this root 2 minus 1, 8. So similarly, this is also called eigenspace. Similarly, for lambda is equal to minus 1. So like this, you can calculate the eigenvectors and corresponding eigenspaces. There's not much time, so let me do one more example only so that you now have a good so I just do one more example and wind up. Then next day, that means tomorrow, we shall take up something else. So one more example, let us say 6th. So let once again the linear transformation be, say, let T the map R2 over R to V, and V is equal to xy goes to Vt, that is xyt is defined by the basis vectors by the basis say B, V1, V2 and V under T, that is V1T, V2T as. So V1T, let us take this is 5V1 plus 6V2 and V2T is defined as 7V2 with a negative sign. So we have the linear transformation, this T. So first thing is that you can determine T. So V to V, so this is here V as xy going to Vt, xy of T, and this I leave for you to determine this. This is for you. That will determine Vt. And you can see that this Vt is, if you write, whether you write in terms of xyt or you write as alpha 1 v1 and alpha 2 v2. So if you write this as alpha 1 v1 plus alpha 2 v2, then in terms of vectors, and if you write xy, then that will be in terms of the standard basis vectors. So if you use like this, then this will turn out to be, but that is for you to verify 5 alpha 1 v1 plus 6 alpha 1 minus 7 alpha 2 v2. So verify, that is very good. And Vt is equal to lambda V, if V is the characteristic vector. So if non-zero V here is, let us take alpha 1 V1 plus alpha 2 V2. In V is such that Vt is equal to lambda V, then you get that lambda alpha 1 V1 V1 plus lambda alpha 2 V2, this is equal to 5 alpha 1, this is lambda V, 5 alpha 1 plus 6 alpha 1 minus alpha 2. If you write lambda V first. And writing this as a linear combination of V1 and V2 and using again as we have done earlier, that V1, V2 are basis vectors and therefore linearly independent, and that the linear combination should give the coefficient of V1 and V2, both of them to be 0. So this will force that lambda minus 5 alpha 1 is 0 and minus 6 alpha 1 plus lambda plus 7 alpha 2 is 0. And the non-trivial solution for alpha 1 alpha 2, only non-trivial solution for alpha 1 alpha 2 is possible when lambda equal to 5 or lambda equal to 7. So the characteristic roots characteristics of P are 5 and lambda equal to minus 7. And likewise, you can find out characteristic vectors corresponding to these characteristic roots of T. That is find the non-zero vectors V such that Vt is equal to 5V and Vt is equal to minus 7. Also find out characteristic spaces T with respect to lambda is equal to 5 and lambda is equal to minus 7. I think enough examples are done, so we shall wind up here. Next time, tomorrow, when we meet, we shall discuss something else. So, thank you very much for your kind attention.
Thank you, sir.